Well, Charlie, I guess we're safe here in this circling pattern.
Right, Ed. But those wave pulses have an incredible amount of energy. We've got to use them to get out of here.
Sure, Charlie, but how?
So far, we've seen that the sine and cosine curves are almost identical. They're just out of phase with each other by pi over 2 radians. Regardless of amplitude, period, or phase shift, curves which have the same shape as a sine wave are called sinusoidal waves. We can find the equation of a sinusoidal wave from its graph alone. We'll use the general equation, y equals a sine kx. We can see that the amplitude is half this distance, 2. So a is 2. The period is this distance, pi over 2. We know that the period is 2 pi over k. So pi over 2 must equal 2 pi over k. Solving gives k equal to 4. Therefore, the equation must be y equals 2 sine 4x. Up till now, we've labeled the x-axis in terms of pi. Now it's labeled with simple integers, and we can still find the equation for a curve. Using y equals a sine kx as a model, a is 3. The period of this wave is 8 units. Therefore, 8 must equal 2 pi over k. K then is pi over 4. The full equation is 3 sine pi over 4 x. We can use other units on the x and y axes. For example, to describe the action of an electrical generator, we use time t and voltage V. What's interesting is that the electricity is produced in the form of a sine wave. This is not too surprising, since the action of the spinning armature matches the motion around a unit circle. A sinusoidal wave illustrates why we call the electricity in our homes alternating current. The voltage alternates between positive and negative values. The actual time it takes for one complete cycle is 1/60th of a second. This means there are 60 cycles every second. Let's look at one cycle. We want to find the equation for household voltage, so we need the amplitude, half this distance. We know this should be 110 volts, but looking at the first half of the cycle, the voltage changes from 0 to some peak value and back to 0. To get an effective value of 110 volts, the peak must be higher to compensate for when the voltage is below 110. Actually, the peak value is 155 volts, and the alternating current swings between plus and minus peaks of this value. Let's use the equation V equals A sine kT, where V is volts and T is time in seconds. The amplitude is 155. The period is 1/60th of a second, so 2 pi over k equals 1/60th. K is 120 pi. The equation that describes the electricity wave is V equals 155 times the sine of 120 pi t. Now is a good time to define frequency. The frequency is the number of cycles per unit time. In the case of the electricity wave, 60 cycles were packed into 1 second. And indeed, that's the frequency, 60 cycles per second, or 60 hertz. A common place where we run into frequency is on the radio. When we tune in our favorite station, we're choosing a sine wave that has a specific frequency. The AM dial is marked from 530 to 1,600 kilohertz, from 88 to 108 megahertz. Now let's look at the motion of a bicycle. The wheel has a radius of 40 centimeters and rotates every 0.8 seconds. We'll draw a graph showing the height of the air valve above or below the axle. The y-axis represents height and the x-axis time. We'll try to find the equation that describes the motion of the valve. With the radius 40, the amplitude of the curve is also 40. With the air valve at its highest point, the curve starts at plus 40, and we know that one cycle ends at 0.8 seconds. The wheel will complete one revolution here. The lowest point will occur halfway at point 4. We can now sketch the curve. It's a cosine function. But instead of y equals a cos kx, we'll use h equals a cos kt, because we're using height instead of y and time instead of x. The amplitude is 40. The period is 0.8, which must equal 2 pi over k. So k equals 5 pi over 2. And finally, the equation for the height of the air valve is h equals 40 cos 5 pi over 2 t.
We have a signal generator, Ed. Let's see if we can get enough amplification to produce some sine waves of our own.
It's working, Charlie, but our wave pulses aren't doing any good.
Sure is strange, but I'm starting to believe that anything can happen inside a black hole.